Good morning. Welcome to Krishna's classroom. What we propose to do today is to give the statement of the main theorem that we want to do in this section, namely the Riesz representation theorem. In fact, all the topological work that we have been doing all along had been to support the statement of the theorem as well as the proof of this theorem. As we shall see, the Urizon's lemma plays a major role while proving the statements of it. Okay, but before we give the statement, let me just motivate what exactly is the problem. Now, you take the Riemann-Stieltjes index. So, let x be. Now, we take Riemann-Stieltjes integral. So, let me just write here. So, we begin with a look at the Riemann-Stieltjes. We have done this elaborately. We begin with x equal to interval A. Now we define a monotone function alpha to r which is increasing and and we shall assume that in fact we can relax this condition, assume that alpha is continuous. In fact, we can relax it and give some discontinuities at a countable set of points and so on. So these are all technicalities which we have considered earlier. Now you see that one can rework. So the usual Riemann integral technique is that you partition the domain into a sequence of points. So let P be a partition of AB given by A equal to x0, x1 less than xn equal to b. So this is a set of points such that this condition is satisfied. Now on that, you see our usual Riemann integral is when alpha is alpha x equal to x or alpha t equal or alpha x equal to x. The usual is corresponding to the choice. Alpha x equal to x for every x belonging to it's a monotonically increasing function, and in that case we had the length of the interval xj equal to xj minus. That's the usual case. But now we modify it. The length as follows. We write alpha based length L alpha as L alpha of alpha xj minus alpha xi. Because this is a monotonically increasing function, therefore this is greater than or equal to 0 for every choice of I and j. And then of course the usual technique of finding out the what is called the lower integral and upper integral is considered, and then you get the definition of the integral. So I am not going into the details of that. So we go through the usual process. To arrive at the integral of a continuous function f as now this alpha may not be a differentiable function. It need not be a differentiable function. So if it is a differentiable function and the derivative exists, then you could possibly, then you know that since it's a monotonically increasing function, alpha derivative is non-negative, and you can write this part can be rewritten as alpha derivative dx. That is possible, but we are not interested in that right now. Okay, therefore you see that you compare this with, suppose alpha x is identically equal to x, what will happen? You will get the usual integral. Okay, so integral of alpha turns out to be this. Okay, what is this? This is something that belongs to a real number. I mean, if you are using a real valued function, then you get this real number. Otherwise, if you are using complex valued function, then you get a complex number. Okay, and you also observe that if f is greater than or equal to 0 on AB, then I alpha f is greater than or equal to 0. Okay, and you see that you take all functions, so you take the space CAB you know that CAB is the space of all continuous functions defined on the interval AB is a linear space. And one can obtain a linear function on CAB defined as follows. As follows. I alpha maps are okay, and I alpha is linear. The first part says it's a functional, therefore it's a functional on this linear space. So I alpha is a linear, and therefore it is in the dual of CAB. It's an element of the dual of CAB. So I alpha belongs to Cx prime the dual space of X, where okay, so it's a linear function. Now you are doing a very versatile thing. Going from the usual Riemann integral, we have now generalized. Now you see that we have what we have done is we have completely redefined the concept of length using alpha. So this is AB. Now this is x dot x1 xi plus 1 and so on. This is equal to xi. Now you see that the length of each of these intervals is involving alpha. Okay. So if you have in some region if alpha is a constant, okay, then what happens? Suppose you take any interval containing that region. Suppose f alpha is constant on CD contained in AB. It is possible because all that you need is it has to be a monotonically increasing function. So it could be something like this. So the graph of alpha could be something which in some places becomes a constant. In that case, what happens? You see that We'll use k because I'm using c here. K a constant. Then for length of equal to alpha which is equal to 0. And therefore, you see that in the integral, CAD integral this is equal to 0. So, no matter what f you use, you are going to get 0 then. So, you see some versatility has been brought about in our integration. Now, this is the purpose of Riemann-Stieltjes integral. So, from the Riemann integral, you generalize to Riemann-Stieltjes integral and became very versatile to accommodate many situations that you come across. And then, of course, because of some inadequacies, you developed what is called the Lebesgue integration theory to overcome that, and by defining a measure. So, what exactly is happening? What is this? See, L alpha of L alpha of CD defined as D alpha D minus alpha C, which is greater than or equal to 0, assigns a new length to the interval CD. The usual length is D minus C. But now this is going to be alpha D minus alpha C, which is greater than or equal to 0. So this assigns a new length to the interval CD given by so that is what happens. Okay. So the complete concept of length has been redefined. For instance, I will tell you something. Okay. Suppose it's a time interval that you are considering. So from time A to time B, we are making or traveling. Okay, right? We are moving. So you consider this as a time interval. Okay. And then consider a car moving from starting at some point at time A and moving along the paths up to time B. Okay. So suppose a car moves from a point P joining them. Starting at time t1 equal to a or t equal to a and ending at t equal to b. So that's a journey that you are undertaking from time A to time B. Now you see, when the car moves, car is not moving at the same pace all along. But we ensure that it is moving forward. Now start measuring the distance. So at time t, so we define a function alpha t. So for t belonging to define alpha a equal to 0, alpha t equal to the distance travelled from P to the point alpha t to the point alpha t. Okay, right? And this you define for every t. That defines the alpha function. So alpha function will be something like this. You plot this alpha function. See, it is going to start at 0 because the distance traveled 0 at that moment, and then it start moving. So it may be, but you see that the distance is always it is not, we are assuming that the car is not traveling backwards. Therefore, it moves up to the distance. This is your alpha b. This is alpha a. Alpha a equal to 0. Alpha a equal to 0. Alpha b is this. Therefore, the total distance traveled is actually alpha b minus alpha a. But it is not traveling at the uniform speed. Okay, so it travels at some speed for some time and then reduces and keeps fluctuating. So it fluctuates, but you see that the distance traveled is always positive, not negative. Okay, because we are assuming that the car is not going backward. Okay, so the distance traveled is always non-negative, and distance function is a monotonically increasing, or at least it is not monotonically decreasing, not monotonically. Non-decreasing. This is something that we are trying to work out. Okay. Now this is a type of alpha that you come across, and then you can build up a dynamical scenario using this alpha, and say relating to the fuel that you consume or some such thing can be used and to define it as in the form of an integral. Therefore, you see that I alpha of f is some continuous function. This is always positive whenever f is greater than or equal. Therefore, it's a positive linear function on CAD. This is the scenario that we are taking. Therefore, we have generalized the concept of Riemann integral to Riemann-Stieltjes integral to accommodate these kind of situations. Now let us come to the problem. The problem is the following. So here alpha is mapped to given alpha, we have got f belonging to is mapped to some scalar integral alpha belonging to R. It's a linear map. This is I alpha. So I alpha is a linear. And hence determines a linear function positive in the sense that if the function f is positive, is non-negative, then the integral is also positive. That's the meaning of that. Positive linear function on CAD. Now at this stage, the question that you ask is the following. Suppose lambda is a linear function on CAD Suppose this is given, which is positive. What he says is that given alpha monotonically increasing and non-negative, therefore non-negative, and through the integral I alpha if is a real number for every f belonging to C alpha, so it defines a linear function which has the positivity property, which is given by this. Okay, but we are now asking reversing the question. Okay. So does there exist a measure? Now you see the distance, the new distance that we have defined. Actually, see, alpha d minus alpha c is a new measure. New is a newly defined distance for interval C. I am just ignoring the finer aspects, like what happens if CD is an open interval, or CD is one side closed, the other side it is open, and so on. In all these cases, this will turn out to be the scenario. Okay, so that is not important to understand the problem. So the question that you ask is, given lambda, okay, does there exist a monotonically non-decreasing function alpha such that lambda f is equal to integral a to b f alpha. So given alpha, you can define a linear function. Now you are asking the question, given a linear functional, does there exist an alpha? So we are asking the inverse question, namely, does the linear functional, then which has the non-negativity property or the positivity property, determine a new measure on the interval AB given by alpha such that lambda f is written as integral a to b f dr. Okay. Is it possible to connect these two ideas? That means on the one side you have the linear functionals, on the other side you have the monotonically increasing functions. So can you connect these two? You know that given alpha, there is a linear, determines a linear function on CA. Conversely, suppose you have a linear functional which is non-negative or positive linear functional defined on a CAB. Is it represented in the form of an integral through a new measure or a newly defined concept of length of intervals for all subintervals? So this is the question that you are asking. So I hope the question is clear. Now we raise this question in the general context. The general context is this. I mean, as I state the theorem, it will be clear what the general context is, because we have gone quite farther away from there. We have come quite a distance from there by introducing the concept of measure, and then trying to represent integrals in terms of measure and so on. So we have successfully done that, and now we are in a position to ask the corresponding question with, instead of a monotonic and increasing function, we will be talking about a measure. This is essentially defining a new measure on it. Okay, so we are going to ask the general question here. Okay, so let me just now just state the theorem in the general. So you compare the scenarios. Okay, what is it? Okay, what is that you have? So let me state the theorem now. Now we are in a position to state the theorem, the statement of the theorem. That probably motivates the question. And now we try to put it in the most general context and try to give an answer to this. It appears you have such a connection, and we are trying to explore that in the general scenario. So this is the Riesz representation. This is a Riesz. It's a statement of that. Let X be a locally compact Hausdorff space. Corresponding to the corresponding thing that you have is the interval AB. Okay, and you know that it's a part of the real line, and this has all these properties. Okay? It's in fact compact, but you can possibly generalize it on the whole interval minus infinity to plus infinity. Then you will be talking about a locally compact. So we are taking the general scenario. Okay, so it has a nice separation property that is given to points which are not the same in this space. You can separate them using open neighborhoods. So that is the concept that you have. And local compactness is for each point there is a neighborhood whose closure is compact. So these two properties are there. Let lambda be a positive linear functional on CCX. CCX is the space of all continuous functions, continuous complex valued functions defined on X. Okay, so CCX is the space of all complex valued continuous functions defined on the set X with compact support. Okay, so that I will list out later what exactly the notation stands for. And what do we mean by a positive linear function? So there are two things here. One was the continuous and support of F is this is CCX. And then positive means for non-negative functions. CCX we have lambda f greater than or equal. Okay, so these are the two conditions that we are imposing. Now, before that, let me say what is CCX. CCX I have already said, and CCX is a linear space. Okay, so it's a linear space, and you can certainly define a topology. So on CCX, the usual topology, and then you take what you call the map lambda from CCX to C. In general, lambda is a map from. Okay, I'll list it out later, but let me just mention this and then probably write down all these details towards the end. Okay, so let me do that. So lambda is a map from CCX to C. So lambda is it's a complex value, and lambda is linear on the linear space CCX. So it's a linear function. Then what the theorem says is, then there exists a sigma algebra M on X. That is, M consists of subsets of X having the properties to be a sigma algebra. So this is a sigma algebra. It's a collection of sets in X. Okay. So this is having that property to be qualified as a sigma algebra. Okay. Which contains all Borel sets. What are the Borel sets? Borel sets are constructed out of open subsets of, you know that on X there is a topology, or what you call the sigma algebra containing all open sets is a part of this script M. That is, the X is contained in that means what? It is the smallest sigma algebra containing all open subsets of X, and this is contained M. And there exists a unique positive measure U on M, which represents lambda in the sense that lambda F is equal to integral over X F for every F belonging to, this is the connection. That means given lambda, there exists a sigma algebra on X denoted by script M, and okay, that is induced by lambda, and a measure mu, a positive measure mu on that, such that integral over X F d mu for every F belonging to CCX lambda. So given lambda, there exists a mu. In fact, there exists a script M and there exists a measure, which is a positive measure, and with this positive. So this is the representation thing. So now just compare this with what I have been telling all along about the Riemann simplicity. There you are talking about corresponding to lambda. So that alpha's position is essentially taken up by mu, and of course it is now in the most polished language that we have used. Earlier we had just worked on intervals for the Riemann series integral, but we have traveled far beyond from there and developed the concept of measure, and what is called by introducing a sigma algebra on a set X, and then a measure on X using this sigma. Okay, so this is what we have, and with the following problem. Nice representation here. What is it? This is called by A, then B is mu of K is finite for every compact set B or C for every E belonging to the sigma algebra M. We have mu of E defined as mu of E turns out to be infimum of mu E mu B with E contained in E and mu. The measure of E turns out to be, you pack E into open sets. Okay? And then for open sets, the measure is defined. Mu is defined. Now you take the infimum of all those numbers over the V's that contain E open. That turns out to be what is called E, the measure of. Okay. D. The relation mu E equal to supremum of all mu K where K is contained in E and K compact. This is another version of this. Holds for every open set E. Because this definition is well defined. That's what it says. Because if E happens to be an open set, then it's going to be measure of. And what more you have? And for every E belonging to M, with measure of E. So this relation gives another way of expressing. Okay. Now the next one, E is an element of M, A contained in E, and mu of E equal to 4 implies What it says is the completeness of the measure. Okay, says that if you take any set of measures 0, okay, then all its subsets are measurable. And the measure of and all its subsets are measurable in the sense that all its subsets are in M. And obviously, measure of A is going to be equal to. Therefore, this is the completeness of the measure. So this talks about completeness. Okay. So what have we, in the nutshell, what exactly we have proved, or sorry, what we have stated. The Riesz representation theorem says the following. So let me just put it, without making sequence pronounced. What you have is lambda is a linear function defined from CCX. That is the first thing. It's a linear function on it is positive. It's a positive linear function. Okay. Then what we assert is that there exists subsets of X which is a sigma algebra, and a positive measure mu such that integral over X so we are associating lambda measure. So what we have is X is now endowed with a sigma algebra and a measure. So that this induces a sigma algebra and a measure which is positive measure on the face, and then lambda f is represented by this integral. Okay. Now there are a few remarks that you have here. There are questions like when they satisfy this kind of relations, or what would be the measure of, because you know that this contains all open sets of X. Okay. In fact, therefore, being a sigma algebra contains all Borel sets. What are the Borel sets? It's the collection of Borel sets forms a sigma algebra, which is the smallest sigma algebra that contains all open sets. Okay, so this is the sort of to bring a synergy between the topological structure and the measure structure. So you see, you have two things here. Let me just point out this. Now you have X locally compact space and you have a CCX and we have to see lambda positive. These are the conditions that we have. Then it induces on this a sigma algebra M and a measure mu. Okay, and M contains all open sets. What does it mean? What are the open sets? The open sets form the topology of X, or in other words, it's a topological space. It's a locally compact Hausdorff space means there is a topology under which this has the property that is locally compact and the separation property of Hausdorff separation is satisfied. So you have on X there are two structures. One, a topology which is locally compact Hausdorff. Then that gives a linear space, or defines, enables you to define a linear space on that. Okay, and then lambda is a linear map from CCX to C. Lambda positive in the sense that if f is a non-negative function, then lambda f is greater than or equal to 0. So that is, it becomes real and greater than or equal. So otherwise it's a complex valued function. It is linear. What more you have? You have the following. On X now a new structure comes. A measure structure comes. So there are measurable sets and a measure defined. Okay. This is induced by your lambda. So lambda induces mu, and of course mu induces the linear function. Okay, right? And this measure and the measurable sets and measure are in what you call sort of resonates well with tau, because every member of tau is in M. So this property is all elements of tau are now measured. This part. Okay, and then lambda is identified by U. Okay, this is the statement of the theorem as we have done in the Riemann-Stieltjes integral. The same questions we have asked, given lambda, or do you have a monotonically increasing function on the interval, which where the lambda f is written as integral of. Okay. So I think that is clear in all these properties around, and it's a longish proof that we are going to build. Now we begin with proving that this measure is uniquely determined. That will be the first thing. Assuming that it exists, okay, it's an existence and uniqueness theorem. What I want to say is it's an inverse theorem. All inverse theorems are different. Okay, given x, m, mu, okay, you can define the integral, and that integral you can show that integral is a linear function on CC. We are asking the converse question. The converse question is this: given the linear function which has the property that it is a positive linear, does there exist a sigma algebra on X and a measure mu such that lambda f is represented as an integral. Okay, and we also show that we have quite a lot of nice things happening, that all borrowers, okay, belong to the borrower. And moreover, we also prove that mu is uniquely determined. Is unique determined. That is one thing that you prove. When the mu is a complete okay, so these are the things that we prove. It needs a long work because we have to, starting from lambda, we have to first construct script m and the measure, and then essentially prove that script m that you have defined do satisfy all the properties of a sigma algebra, and mu has all the properties of a positive. Now this is our task, and he's going to take probably 3 to 4 lectures to go through the proof, because it's one of the cornerstone theorems connecting us, cornerstone structural theorems that have how linear functionals are associated and how measures determine linear function. That is straightforward. That is what we have seen already. But how linear functionals with certain properties do determine what are called positive measures. So I think I'll stop here. I have given an introduction to the Riesz representation theorem to discuss statement. Thank you very much.